Yeah, it's fine. That is good. Can you see my screen?
Yes.
Okay, thank you. Thanks for confirming. Okay, so what's we did for the last week? Last week actually we saw some operating system and how computer system works, some different levels of memories like register, also RAM, STD, and how they work together. This kind of stuff actually we studied in our first class, and also we saw that there are 5 types of operating system, but apart from this, there is another 2 kinds of operating systems we have discussed. One is called multi-programming OS, another is multi-processing OS operating system. We also find this discussion in our module 1, I think, in this if you go to the module in your class, in here, I think I stopped that thing, so you can canvas, look at the canvas. Yes, go to my account. Sorry, I just stopped that things. In courses, in advanced operating systems, in modules, don't forget to study the module on additional, because this is kind of summary of what we studied actually last class from this module on. I actually recommended to study both of these PDF as well as the PowerPoint slides. Okay, also similar as in here, module 2 and module 2 PDF as module 2 additional. So this is summary. Actually, go through this module 2 additional PowerPoints today's class. Before I start, do you have any question and concern in our last class? Okay. So yeah, last class was kind of introductions. Apart from introduction, actually, I wanted to introduce with you some operating systems that I mentioned. One is for multi-processing operating system, another is multi-programming operating system. So in this class, actually we focus on the multi-programming operating system, because all operating textbook and everything to study the operating system, they follow the multi-programming operating systems. Before I study, before actually started, so what is multi-programming operating system? In multi-programming operating system is nothing but it actually able to do the concurrent processing, multitasking, and also multitasking actually is performed by concurrent processing that's actually resides in our RAM. What does it means? For example, you have you open to 3 different program at a time or software. Let's say your MS Word document as well as one music player. So both of these will be, when you click, and if space is available in your RAM, it will be actually process will be reside inside the RAM, and from this RAM actually CPU CPU actually fetch instruction and execute it. So here I mentioned you open MS Word as well as the one music player. You hear music as well as you are typing. So in that case, what actually inside the operating system doing? It's if you have multi-program operating system, means there is only one CPU present in your computer. Also, it is single core CPU. So uh, in that case, what operating system does, it's switching between two processes when you're typing, and then switch between MS Word and also music players, and actually it is done by concurrently, not parallelly. But due to the speed on your PC, there is no intermittent. You just hear smoothly both. Actually, MS Word type. You can hear the music as well as the MS Word typing. You do smoothly. So this is how a multi-programming OS works. So here is one concept is that uh, if you consider this is the RAM, uh, also you know that operating system is also a software. It's also a program, but it is complex program. So when you start your machine, where actually operating system also should reside, also should inside. It is a process. Also, it should be inside in your RAM as well, right? And also, then you click your process. Also, if you open one software or one program, if user if the space is available, then it will also accommodate inside the RAM as well. There is two things. Operating system is always be actually, if it is inside the RAM, it always takes some space. So this space is also known as the OS space in your RAM, and rest of the space is also known as the user space. In user space, you can use for your process. When you actually open different programs, then it will accommodate into the user space of RAM. Now see, for multi-programming operating system, there is one concept is called degree of multi-programming. So what does it mean? The degree of multi-programming? It is simple. Let me actually explain that things. The maximum number of processes that can present inside the RAM at a time is known as the degree of multi-programming. Maximum number of processes. So you know that process size is also different always. The MS Word, if you open the MS Word, that size is different. Also, if you open Google Chrome, this is also different size. And if you go for the Photoshop, it is also different size. So process size is always variable. It is not fixed. It can be fixed. We don't know. It can be fixed as well. It can be actually similar to another process if size is same. But we can say it is most of the time it is variable. So when degree of multiprogramming says that at any given time, how many process actually inside into the RAM, this is known as the degree of multiprogramming. Number of process. If the number of process inside in your RAM at a time, for example, in this current time, you just open 3 programs and resides inside. If it is resides inside the RAM, degree of multiprogramming is 3. If it is 4, then degree of multiprogramming is 4. This is actually concept of degree of multiprogramming. Also, let's see one example in that. Let me give one example for degree of multiprogramming, then I'll move forward. From here, you can see that degree of multiprogramming is nothing but depends on the size of your RAM. If your RAM size is big, then you can say that the degree of multiprogramming is also a large value. If it is a small size, then degree of multiprogramming is also a less value. Because if it is small, you can easily actually say that, okay, no, number of process at a given time, of course it will be a lower value than if you compared to if you use a large size of RAM. So it's actually highly dependent on the size of your memory or RAM. Let's say your RAM size is 4 GB. So 4 GB is nothing but how many bytes? it is 2 power 32 bytes. Okay, before I start, let me share my screen. Today I will draw some parts in my iPad. So let me stop my video as well. Let me stop my video as well as, yeah, stop sharing. I'm going to share my my screen from my iPad. Okay. It is fine. So I'll switch between my iPad to my laptop. So now let's see. Here I from my share content, I will draw something from in whiteboard. Can you see my screen and whiteboard screen?
Yeah.
Okay, thank you. So what I mentioned, that if your RAM size, let's say this is your RAM, this is your RAM, its size is 4 GB, 4 GB, and let's say your process size for analysis purposes, you say it is 4 KB. Let's say it is fixed. This is process size. Let's say this is fixed size, but it is not fixed. Just for calculation purposes, we actually make an assumption that we have 4 KB process and we have 4 GB RAM. Sorry, GB RAM, 4 GB RAM. So how many process? Let's say 4 GB RAM. Let's say this is total 4 GB and 4 GB for user space, and another 1 GB is for the OS space, user space. Let's say this is total size is 5 GB. Sorry, 5 GB, and 4 GB is available for user space. This is for user space. So if it is, I say the process size is, so how many process at a time we can accommodate inside the RAM? It is simple. So 4 GB, we can say it's nothing but 1 GB means, okay, let's say, let again remind that what is GB KB. For example, 1 KB equal to 1024 bytes. So it is nothing but 10 to the power, 2 to the power 10 byte, 10 byte. And let's say 1 MB equal 20 power nothing but 20 bytes, and 1 GB equal 20 power 30 bytes. So 4 GB is nothing but 4 into 2 to the power 30 bytes. It is 2 to the power 2 into 2 power 30 B bytes, and this is 2 to the power 32 bytes. And our process size is, just we divide by this process size, is 4 KB. 4 is nothing but 2 square into 2 to the 2 power 10. It is nothing but 232 bytes, and also here also 2 power 12 bytes. So byte cancel. So total we can accommodate at a time 2 power 20 process at a time. This is process 20 power. This amount of process we can accommodate for 4 GB RAM is if all process in 4 kilobyte. So we can say that the degree of multi-programming for this system is 2 to the power 20. This is very large number. Do you have any question regarding this? Okay, these simple things. Okay, let's move forward. Our next topic is Today, actually, we mainly discuss about the memory allocations, and we'll see that some different memory allocation algorithms in this class. Let's say before I start, let's again actually recap some basic of memory allocations. What does actually memory mean? If we say this memory, we know that memory it means the our RAM or random access memory, and also our register. It is actually very close to our CPU, and cache memory. Cache, actually, we don't need the cache memory right now for this operating system. For this course of this operating system, we can just ignore right now. It is fine. And also we have disks or we can say HDD. This is our different types of memory. If we draw this, if I draw this, this is here. I say this is our CPU, and in here we have register. Register is very close to the CPU, so there is no memory actually is faster than this than the register. Actually, register is the fastest. We can say the fastest access memory by the CPU. Then we have our RAM, that we can say the random access memory or memory, RAM, and our disks or HDD or SSD. It is both are available, SSD or SSD. This is the RAM. So now let's say how about the register size? Register size is nothing but depends on okay. Let me actually come later in this part. So what actually computer does when you open when actually you open a computer, how actually memory actually is cleared, or how actually memory divided by our systems. It is nothing but some sort of word size. It is called word. This is one word. That is also one word, and like this, divided by a word. In register is also nothing but this is also one word. Here is also one word. This is word size. So now you may ask me that what is the word? This is new topics, new things. So what is nothing but a 16-bit, usually 2 bytes is refers as a word, but it can be nowadays it can be 32 2-byte machines is available. Also, you know that 64-bit operating system, 32-bit operating system is also your system or CPU support 32-bit, also 64-bit. Then you can say your machine is if it is 32-bit means the 4 bytes. Then you can say the double word. Also, if it is 64-bit, then 8 bytes. 8-byte means the word machine. So if it is 64-bit, then then your word size will be 8 bytes. And if it is 32-bit machine, then it is word size will be the 4 byte. And if it is 16-bit, then it is 2 bytes. Okay. So now what CPU does? CPU actually when CPU executes a program, it just copy the instruction into the register. It just copy the instruction into the register. And another thing I have to mention that what actually RAM contains. RAM contains nothing but some instruction, as I mentioned that instruction or and also data. Two things. Two things. What is the instruction means? Instruction is nothing but now you can say it is little bit different. Nothing but you can say the line of a code. One line of a code is referred as one instruction, but it is slightly different when you convert to the to your high level code to the machine level code. Actually, one line instruction, one line code can be to a three instruction. Let me give a one simple example. If you declare a variable in your high level language like int a equal, let's say, assign 20 comma b equal assign 30, but when you convert to the machine, when it is compiled, it will be two lines instruction. Move, let's say ax is on register is 20, and another line will be the move. Let me write in here. This is different line. Move bx. Let's say bx, another register is 30. This is how actually it can be one instruction, one line of code can be more than two or three, more than actually two or three instructions. But in this class, let assumption that one line means as one line of programs refers as the one instruction. And what is the data? Data is nothing but when you actually write a code, you need to read files. Also, you have variables, give some data for integer, whatever data. Also, if you music file, also if you picture files, all are the data. All are the same format, some format as a data. Also, it's loaded. Everything is loaded inside the RAM. Is nothing but 0 or 1. It's binary number or machine code numbers. Okay. So, any question? Okay, let me move forward. So I was in here, and now you can say that how actually machine CPU asks for the data to the RAM. So before I start, what actually our computer system does is word inside the RAM. Here actually I just show you only three or four actually worded words like 1, 2, 3, 4, 5, 6, 7, 8, just for the space. But it is very big. You know that yeah, RAM size is very big nowadays. So for our study purposes, we just consider our RAM contains these eight words, let's say. So how computer CPU acts to the data. Before I actually explain that one, every word in a RAM actually has its own address. It starts from 0, 1, 2, 3, 4, 5, 6, 7, total 8. Every word in a RAM actually addressed by some numbers, unique numbers. It starts from 0 to till your size of your RAM. So it is not a you know that computers it doesn't work with this kind of decimal number. It's works in binary numbers, binary format number. With computer always works in binary addressing of this binary addressing of a RAM. So what is the 0? 0 is address for. Okay, let's see that. So if you have 8, if you have this 7 address, 0 to 8, this 8 address. So how many bits is required to address this 8 8 slot, 8 words? How many bits is required? If it is 1 bit means either 1 or 0. 1 bit can address as two word, two slot. If it is two slot inside the RAM, two word, only two word in our RAM, so one bit is fine. One is for 0, another is 1. This is one bit is fine. If it is 4, then how many bits is required? If it is 4, then you cannot present only the one bit. That time you need, I think, 2 bit, at least 2 bits. 2 bits. So 2 to the power 2 equal 4. Let's say this way, 4. So 4 slot can be to address the 4 words. You need at least 2 bits. 2 bits. How? So if it is go for binary, only binary number already 0 1 0 1. So 0 0 1 1. So this is nothing but 1 2 3. 0 1 2 3. So this is how we can address. So from here you can say that the 2 to the power n actually n words, to address the 2 to the power n words in our RAM, we need total how many bits? N bits. From here you can come up with the 2 to the power 2 2 to the power means the 4 is kind of how many bits is required? 2 to the power 2. If it is 2 power 2, this is 2 bits. 2 bits. 2 bits. So 4 requires 2 bit. So you can also 1 bit. You can also 2 to the power 1. 1 bit you can address the two word, and 2 bits you can address the 4 word. And from here you can say that 2 to the power n, for 2 to the power n words, you need total n bits, at least n bits. So let's see one example. Let's say your total. Also, one thing is that everything in our computer system, either RAM, register, as well as our hard drives, any memory is always order of 2 to the power n. It would be 4 byte, 16 byte, or 32 bytes like this. You have 64 byte, 64 byte RAM, but you never hear that 62 byte RAM. 60 let's say 64 megabyte RAM. You never had the 62 megabyte RAM. It is always 2 power n. This is one more note for this memory application. And then if you also look at that every word inside the RAM has an own address. An address always the binary format, as I mentioned earlier. And also total number of bits represent the memory depends on the size of the memory and what size. What this means, I'm just telling you, I just show you that if your RAM size is, let's say 4 GB. So 4 GB is nothing but how many bytes? 4 GB is if your what let's say your word size is 2 bytes. A 16-bit machine, your word size is 2 bytes. I'm just telling you that it is word is 2 byte size. 2 byte size till 4 GB. Till 4 GB. It is 2 byte size. Word size is 2 bytes. Now let's say how many bits is required for addressing the each word in this memory structure. Let's calculate that things. Here I mentioned that memory size is 4 GB, and also we can say that 4 GB is nothing but 4 GB is nothing but 2 square into 2 to the power 30. This amount of byte means 2 to the power 32 bytes. And also I mentioned that each word size is 2 bytes. So total word of so how many word of this RAM will be? So just divided your total size of the memory is 2 to the power 32 divided by this is also byte. Also our word size is 2 bytes. So here I'll get the 2 power 31 byte cancel. So 2 power 31. So total word inside the RAM is 2 power 31. So to addressing this, so you need total how many bits? 31 bits. 31 bits. Can you get this? It is just continuation of our previous slide, previous things. If you have 4 items, then how many bits is required? It's kind of 2 power 2 equal 4. So 2 power is 2 power. What is the 2 power 2? 2 power if you matches with match with 2 power n, power is 2, so 2 bits is required. In general formula, you can say 2 power n can 2 power n items can represent by n bits. This is so n bits here, 31 bits. So to addressing this from 0 to 2 power 31. 2 power 31 is step from 0 minus 1 by 0 0 0 0 kind of like this. This way, actually we manage our address of a RAM. How many bits is required for addressing the whole RAM. And next step is that, so when CPU asks for a data, in our last slide actually mentioned that how many when CPU asks for a data, so how it is asked? It's asks for a data to store in register CPU. This is CPU, and this is register SR, and this is our RAM. This is our RAM. So how it asks for a data? It asks for the data just using the address of this word. What's actually let's say here is first instruction, here is second instruction, third instruction, third, fourth, fifth, and so on. And when CPU asks for the third number of instruction, he just send the address for here. This is 0, this is 1, this is, if it is binary, this is 1 0, here it is 1 1. He asked for a data by using this address. So it's always asks for a data by using this address, and copy the data from here to the register, and register actually from this register CPU execute your code or program. So how it is sent to the request to the RAM? There is a bus. This kind of stuff is you will study in computer architecture and organization class. So just for give you a rough idea, computer bus is nothing but the connection of wire. It's connect to the RAM as well as the CPU. Here CPU. So here is one address. One bus is called the address bus. By using this address bus, it sends the request for the data from a specific address, and how it's retrieve the data from a specific address by using data bus. It's called the data bus. Another bus is data bus. By using the data bus, CPU collects the data from RAM to register, and then it executes. This is the actually basic steps for CPU, how CPU actually interact with RAM. Very basic things. And okay, now you can see that there there is a sets of address is always, if you see here, it's kind of very big 000 31 bits. 31s, I cannot write this 30 31, then 0, 31 0, then 1 for this address, and goes and so on. This is very this kind of actually address for your 4 GB RAM, if your word size is 2 bytes. If it is 4 bytes, then it will be reduced. If it is your word size is 1 byte, let's say if it is 1 byte, that it will be 2 to the power 32. 2 to the power 32. 32 units, that 32 bits that time. So, the address here, the address of a RAM. So this is the address, as I mentioned. This is the address 0010. This is the address. So this address is known as, this collection of address is known as the address space. It's called the address space. Address space. Also, it is an address for our RAM or memory. This is also known as another special name. Is called the physical address. Physical address. The address of our main memory or RAM is known as the physical address. Similarly, let's open another new page. Similarly, let's say this is your RAM. This is your RAM. Sorry, my drawing is not good. Also, you have some process. Inside the memory, you have some process. Let's say you open two. One is for Google Chrome and one is for the MS Word. MS Word. This is the MS Word. This is for Google Chrome. You click these two programs in your computer, and then your OS is here. Operating system space is here. This is your user space. User space. User space. In user space, let's say here is already some. Let's say this is user space. Here it is start from 00, kind of like this. Also forget this OS space right now. Here for understanding, this is for 001. Here is also and this is OS space. Let's say here is 0000. Let's say 1111, and then some process, and then your MS Office is in here. MS Office, actually this process occupied in this location, and here is, let's say, another space is blocked. Some process already have taken this space, and then your Google Chrome is in here. In Google Chrome in here. This space, let's say 0011110001. Let's say this kind of space in here. This is known as the physical address. Actually, it doesn't change. It is always same. Depends on that your RAM memory size. It is always fixed. This address is always fixed. And also inside the process, also process is also divided in some word wise. Some word. This process is nothing but itself. It is a memory. MS Word, let's say MS Word, it takes 20 MB. So it also split it also in different. Let's say for understanding, one process is, let's say, is 10. Let's say 10 bytes. 10 bytes. So if it is also our assumption is 2 bytes for each word. So 2 bytes for each word. So this process 10 bytes is split into 2 here, 2, 2, 2, 2, total 5 bytes. And here is every process has its own address space or own address. So here you have to address your process slot as well, process word as well. This is also started from 0. This is also from also binary number. Let's say it is I just decimal number. This is also a address space for a process. This is process address space. This is process address. This is process address, and each word has its own address. It's always also GC. This is for, let's say this is for MS Word. Also GS process. It has also 0, 1, 2, 3, 4 like this. So if you consider this is, for example, this is 0, 0, 0, 1. This is, let's say, another 0, 0, 1, 1, 1, 1, 1, 1, 0, 1. Let's say this one. And MS Word also here is also 0. Also here same thing. There is also 1, 2, 3. So 0 is mapped to this physical address, 1 is mapped to this physical address, and 2 is mapped to 2 is mapped to another physical address. Also GC also same. This is 3 here, the 3 word in Google Chrome. So this is 0, 1, and 2. 0, 1, and 2. And also here physical address, let's say let's say decimal number 10, 11, and 12. Here also you see 0 is mapped to the decimal number 10, and 1 is 11, and 2 is 12. So this is the physical. Also this is the process contents also address. It is known as the logical address. So logical address is always match with one, always actually match with one physical address. This slot for MS, this slot for this word for physical physical words actually fill up with from GCs this word. Contiguous. If it is contiguous allocation, we'll come up with contiguous. So so far you have to understand that what is the logical address and what is the physical address. The address in a process is known as the logical address, or the address that in our RAM is called the physical address, and address in our process is known as the logical address. Process address is called logical address. So now you know the 3 things. One is the address space. Address space is nothing but a collection of address. It can be both physical address as well as the logical address. Physical address means the the address for our memory or RAM. This is the physical address. And logical address, the address for our process. This is the logical address. And CPU always asked data by using the physical address, not logical address. Later we'll discuss elaborately. CPU always asked to the data by using the physical address of RAM, not logical address. If it is logical address, then CPU won't find the actual value for data. Now we know the address space, and our next is we'll talk about different memory allocation system. How we allocate our memory from our. This is kind of I just give you the overview due to understand our next algorithms and everything. You need always the physical address, logical address, this kind of stuff. You need to understand this kind of stuff. That's why actually I give an overview overview that what is logical and physical address, so that later we can understand. Any question? Okay. Thank you. So let's move forward. So what is the memory allocation? It is nothing but to allocate memory inside the RAM. Inside the RAM, there is two kinds of memory allocation. It is one is contiguous memory allocation. Memory allocation. Let me start. Allocation. Another is non-contiguous allocation. Non-contiguous allocation. Allocation in contiguous allocation, it has also two parts. One is for fixed partitioning. Fixed partitioning, or static, also known as the static partitioning. And another is variable partitioning, or also known as dynamic partitioning. These are the two types for the contiguous memory allocations. And also one other is non-contiguous allocation. Let's see that what is the contiguous memory allocation. In definition, the contiguous memory allocation is all the address of logical addresses space are placed in contiguous of the physical address space. What does it mean? All address of logical address space. Logical address means the process address space for any process. This is the address space, let's say, for a process 0, 1, 2, 3, and this is our RAM. Let's say this is 0, here is 1, 2, 3, 4, and 5. So what does it means that this process should be contiguous in the physical location. So if 0 is start from the 2, so process should be reside from 0, 1, 2, 3. This in here 0, 1, 2, sorry, till here 3. So this is contiguous with the physical address. It is not like this. This two word is in 0 and 1. 0 and 1. This process, this part is in here, and another this part is comes to here, and between this there is another process. It is not like this. It always map with the contiguous address of physical address space. This is logical address space. This is physical address space. So when you actually when you allocate a memory for this process, let's say this is process P1, so it should be always continuous with the physical address. This is contiguous allocations, and non-contiguous is just opposite of contiguous allocations. Here, the all address space of logical space are not contiguous in physical address space. Means that in this allocation, for this process, here is 1, 0, and 1, 2 word is in that location. For here is, let's say, this is physical address, this is logical address, this is logical, and this is physical. Also here some 2 takes another process. Also 3 also, it also, let's say, takes another process. And and the rest of them are inside this is 3, this is 4, 5, let's say 6 in here. Here already get the allocation for 0 and 1, and next 2 and 3, let's say in here. Here is 2 for logical and 2 for 3 for here. So some part of our logical address space actually it is not, you see, it is not allocated in a contiguous location in our memory. Some part is allocated in different location and other part is allocated in other locations. And between this process, between these addresses, there is kind of another process maybe available there. So this type of memory allocation is called the non-contiguous allocation. And contiguous allocation is always be contiguous memory within the actually physical address space. You cannot actually divide your process in two parts, and between this process there won't be another process there. So this is for contiguous and non-contiguous memory allocations. And let's say let's start that what is the fixed partitioning. So before we start fixed partitioning, any question for contiguous allocation and non-contiguous allocation? This is important. So this is it is understandable from its name as well. Okay, let's move forward. Here we know that in contiguous allocation there is two kinds of allocation type. One is the fixed partitioning, another is variable partitioning. Let's see what is the fixed partitioning. Let's say this is your RAM, this is your memory. When you start your computer, actually in the starting time, you have to we have to divide our memory in kind of fixed slot within fixed partition. Let's say this is 2 MB, 2 MB. This is we divide our partition. This is 2 MB. Let's say this is for 4 MB megabyte. This is, let's say this is 6 MB. This is 5 MB. Megabyte. So how many MB? 6, 12, 12 and 17. Okay, this is just for an assumption. You know that nowadays memory size is very big. Just for assumption that this is the partition size for our RAM when you start the computers. Actually, we have to divide our RAM in fixed partition. We cannot change it. We cannot change this partition later time. It is always fixed. So this is the basic concept of fixed partitioning. So what is the problem in here for fixed partitioning? Let's explore that things. Let's say you have a process. You have 4 process. Process P1. Process means that program you just click or you just want to run in your computer. Process, different kind of process. It could be MS Word. It's kind of when you can click, this is MS Word process. Microsoft PowerPoint PPT. If you click, this is another process. Create another process. Also, if you run any program, this is one process. If you want to hear music, music player is kind of another process. This is the process. Different kind of process or program or software, whatever it is. Kind of let's say this is similar things. And now we are talking about the fixed partition. Fixed partitioning. Fixed partitioning. How it works? Fixed partitioning. So I said that you have the 4 process. Let's say one is 2 MB. This 2 MB is accommodate that place in your RAM. Let's say you have a process for 10 MB. 10 MB. So can you fit this process in your RAM? So you cannot. There is no slot for 10 MB. Here is maximum is 6 MB. So you cannot go beyond this 10 MB process. This is one kind of limitation for fixed partitioning. From here you can say, always from here you can see that there is two things for two rules for fixed partitioning. One is that a partition can hold only a single process. A partition can hold only a single process. For example, here is the 4 partition. So it can hold only maximum 4 processes. You cannot do that. Okay, if it is, let's say again, you have the 2 MB 2 process, 2 MB. Another is also 2 MB. 2 MB. So first one, you just put it in here. It takes 2 MB space, and then another is 2 MB process comes in here. So can you actually allocate for this process in here? You cannot do this. This slot is already taken by this another process. So even though here is 2 MB is available, but this in this slot there is another process is already available. So you cannot insert another process in this slot. You have to go another slot. Another slot for 2 MB. You cannot do this 2 MB. So in this is actually here means that partition can hold only a single process. Only a single. Each partition can hold maximum 1 process. Also, a process cannot pass over more than 1 partitions. What does it mean? Previously, I said that it is 10 MB process. 10 MB process. So here is 6 MB. Here is let's say again. I just make some. Yeah. Okay. Here is 6 MB. Here is 5 MB. So you may think that okay, 10 MB, 6 MB will you have to actually allocate 6 MB in here. Also another 4 MB you will allocate another partition. But for fixed partition you cannot do this. You cannot actually pass over more than 1 partition for a single process. This is the another limitation for our fixed partitioning algorithms. Sorry, allocations. So another thing is that you see here is 4 MB size, but you just here actually you allocate for memory for 2 MB. So 2 MB is kind of unused. You cannot use these spaces. This is unused space. You can use this process if it is a process has if process is completed, then memory will be deallocated. Then you can use for another 4 MB process. It is fine, but when a process 2 MB is in here, that time 2 MB is useless. You cannot use this 2 MB. It is just wasted. It is just wasted for a fixed memory allocation, fixed partitioning allocation. So this is also known as a special name. It's called internal fragmentation. It is called the internal fragmentation problem. Internal fragmentation problem. So what does it mean? Even though you have the enough space, let's say this is 4 MB. Also, you have the 2 MB process, 2 MB process. You allocate first process for 2 MB. That is 2 MB is available, but you cannot allocate for this 2 MB for this new process. So this space is always wasted, and this is known as the internal fragmentation problem. So For fixed partitioning, we also we have got several problems like problems of disadvantages. It has internal fragmentation problem, and the process size never goes beyond the maximum partition that is told you the 10. Here is maximum is 6 MB. Partition size is 6 MB. So you never go beyond this 6 MB process. Huh? You can accommodate maximum process size as 6 MB, not 7 MB, because maximum partition size is 6 MB. And next is degree of multiprogramming is limited. Degree of multiprogramming is limited. What does it mean? What does degree of multiprogramming? Degree of multiprogramming means that number of process you accommodate inside a RAM. Here you already partition for partition. So you never go beyond this for degree of multiprogramming programming from 4. It will be maximum 4. Now it's equal to the number of partitions. So degree of multiprogramming equal to number of partitions. So it is always limited or fixed for fixed partitioning systems. So we have little bit time, so let's talk about little bit about the variable partitioning. So what is variable partitioning? Variable partitioning actually when you open this computer, your RAM is totally, let's say your RAM is free. Of course, there is OS space. OS space there. It is fine. OS is in here. Okay, and when a process, when you create a process, let's say 2 MB, 2 MB just accommodated here, 2 MB in here, 2 MB in there. And again, it is, if it is, again, you create a process for 5 MB, then 5 MB will be accommodated here, let's say 5 MB. So it depends on, in here you didn't actually make a partitioning. You didn't make a partitioning. It depends on the process size when you create the process. When it creates the process, actually, then it will take the space from your RAM or from your memory. So it has also some disadvantages or problems. Let's see what are the problems in here. First, let's okay. Okay, so here the partitioning time size depends on the process size. This is your disk. Whatever program you open or process you open, it has some size. Let's say 10 MB. So it will take the process for this space from here 10 MB, and then again you create another process for 2 MB. 2 MB. It will take the, let's say, it takes the process for space from this 2 MB, 2 MB, and then 10 MB. Let's say again you open another program, 10 MB. Here is, let's say, 10 MB. 10 MB processing here, and another is 2 MB. 2 MB. This is for, here it takes the process problem for 2 MB, takes the place, takes the space from your RAM 2 MB, and let's say this is for 15 MB, another process already in here, 20 MB, let's say 20 MB processing here. So after sometimes later, this process completed and deallocated the memory. Also, this 4 MB is also called completed process, completed and deallocated the memory from your from your RAM. Deallocated the memory. You know that when a process is completed, then it's a release the memory. This process is completed and also release the memory as well. So these two slot, this is here is 2 MB, here is 2 MB. Here is process is available. Here is process is available. Also here is process is available. Now we have 4 MB. 4 MB is free. Here is 2. Here is 2. Total we have 4 MB free space. 4 MB free space. So next, let's say another. You click another process, whose size is exactly 4 MB. 4 MB. Now you can say that 4 MB can be placed in 2 different locations. No, answer is no. You cannot do this because this is a contiguous allocation. This is a variable partitioning, but it is a method for contiguous allocation. If you actually divide your process in 2 MB and 2 MB, 2 MB in here, 2 MB in here, it is not a contiguous actually address. Contiguous between this process there is another process, so it is not a contiguous location in your physical address or RAM. So you cannot do this, even though 4 MB space is available, but due to the contiguous constraint, you cannot place the 4 MB inside your RAM. So this is a kind of problem. So there is holes is always created in your variable partitioning system, contiguous variable partitioning systems. Hole is always be created. Not always, is always be created. We don't know. But this is a problem for variable partitioning. What does it mean? So what is the advantages in here or disadvantages? There is no internal fragmentation. You know that process size is equal to your memory size. So there shouldn't be an internal fragmentation. Also, maximum process depends on the size of your RAM, not size of the partition. So here we take some time, some space, but all user space. If your process is, let's say 10, 20, 30, 34 MB, 34 MB, let's say this RAM size is 40 MB. If your process size is 30 MB, all user spaces can take. It doesn't. There is no limitation for by the partition like the previous one, fixed partitioning. You cannot go beyond your maximum partition. But here is not that kind of constant. But your process can as big as your RAM size, your memory size. And another thing is that degree of multi-programming is not limited by the fixed partition. Because what is the degree of multi-programming? Number of process inside the RAM. If it is very small process inside the RAM, you see that you can occupy all of these spaces and you can fit many processes at a time inside the RAM. So degree of multi-programming here it is not fixed as a number of partition like the fixed partitioning system. If it is fixed partition, you can. If it is 4 partition, you can insert at best 4 process at a time. But here you don't have this kind of constant in here. Another problem is that there is no there is external fragmentation. You know, this is whole. There is also whole. Even though 4 MB space is available, you cannot fit the 4 MB new process inside your RAM due to the constraint of contiguous memory allocations. So this problem is known as the external fragmentation. External fragmentation. This problem is called as the external fragmentation problem. So is it possible to external fragmentation in your fixed partitioning? Answer is no. There is already you fixed your partition. So whenever a process comes, it just occupies the memory. It's never go beyond the process size, beyond the partition size, but there is no actually external fragmentation. Here you see this is, let's say this is 4 MB. Here is also whole as internal whole for 2 MB. Also let's say this is 6 MB size. Here is 4 MB processes already take the place and 2 MB is available. But when the new process comes for 4 MB, here there is let's say all other is occupied, and new process comes for this 4 MB. Here is 2 MB, here is 2 MB. You cannot fit this, but this is not the actually external fragmentation. This is internal fragmentation. This is inside a partition. It's always been happened inside the partition. So this is why this is called the internal fragmentation. But for variable partitioning, your actually memory may suffer from the external fragmentation. So any question? Sorry. Okay, let me stop in here today. And for any questions regarding the partitionings or anything, you may ask me by the email. Yeah, email me anytime. I am here. Also, you can see that I also make one. In syllabus, I updated one thing is that office hour is 7 p.m. till 8 p.m. at Friday. You can use my Zoom ID. That is, you will find it in syllabus. Okay, thank you. So we may stop in here and see you next time. Have a good evening.